My name is Michael Klein. My pronouns are he, him, and I am the Software Development Tech Lead in Northwestern University Library's Repository and Digital Curation Workgroup. I'm speaking to you from Northwestern's campus in Evanston, Illinois, which sits on the unceded lands of the Council of the Three Fires, consisting of the Ojibwe, Potawatomi, and Odawa people. Today, I'll be talking about our transition over the past several months to a largely cloud-based development environment hosted on Amazon Web Services. I'll start with both an apology and a gentle warning. This talk is fairly jargon-heavy and veers off pretty sharply into the ops side of DevOps. As much as I hope that the next 15 minutes or so will have at least a little bit to offer most of you, it definitely goes from zero to nerd pretty quickly when I hit the 5th or 6th slide. Though I suppose nothing I do ever starts at zero nerd, but let's just say it'll ramp up. I'm not going to dwell on this slide for too long, but I wanted to share just a little bit of an overview of the dependency stacks that support our three main backend applications, 2 built on Samvera frameworks and 1 built in Elixir. This doesn't even get into our front-end React applications, APIs, or other services, but you can see that we've got a whole lot of dependencies, a lot of which are hard to emulate locally. I started making slides detailing how we got to this point, describing each of the Docker container-based dependency stacks and accompanying homegrown tools we've used over the past 4 years. Then I realized I could easily run through my whole 20 minutes and never get to my topic. So this is all of the deep historic overview you get today. There's not a lot in here that was important, but it's just to make it clear that we've been through a lot of different options over the years. Our team of 5 developers maintains several different applications and APIs with different dependency stacks. As our software ecosystem has moved more towards serverless applications, functions, and services, it has become increasingly difficult to maintain a laptop-based development environment that can adequately replicate or emulate the entire suite of dependencies we rely on. We also found that our architecture decisions were becoming constrained by the need to run or at least connect to everything locally. To that end, I set out to build a fully remote development environment inside an AWS EC2 virtual machine. It relies on a combination of shared and individual resources, shared for things that won't interfere with each other during simultaneous use, and individual for things that need to be kept separate, like data storage and message queues. Each developer has a dedicated instance for their own use that boots itself up on demand and shuts itself off when idle. Since AWS only charges for EC2 instances when they're actually running, the idle time shutdown helps keep the cost of the service as low as it can be. The primary goal in building this tool was to create an environment where the entire breadth and depth of AWS services could be available to us to experiment with and incorporate into our application stack as needed. But another very high priority was to allow each developer on the team to continue to work to the greatest extent possible with the same tools, customizations, and configurations they're already comfortable with. Last, but certainly not least, was the need to create something that was relatively easy to stand up, tear down, and maintain. The core of the environment consists of an AWS virtual private cloud split into 2 subnets, one internet-facing public subnet and one fully firewalled private subnet. Each developer has a dedicated virtual machine located in the public subnet that can access resources on both sides of the firewall. By default, there are no open ports in the security group containing the EC2 instance, not even the SSH port used for connecting. All connections are made via an AWS Session Manager connection, which is able to open an SSH section on the virtual machine without an open port. This is the part I was warning you about earlier. The piece that makes this IDE-based development possible is the Visual Studio Code Remote SSH plugin, which installs a full headless copy of Visual Studio Code on the remote machine. The entire VS Code environment, including extensions and settings, runs on the server while using the local copy as its user interface. The remote VS Code server inherits the local settings, but can override any or all of them, making it easy to differentiate local and remote windows by using colors, fonts, and themes. One of the primary seamless convenience features built into the dev environment is that the SSH client can trigger it to boot up if necessary. This is made possible through the use or possibly misuse of the SSH proxy command configuration option. Normally, it's used to tell an SSH client that we have to connect to one server by first connecting to another and proxying the connection through it. But in our scenario, we're telling SSH, whenever someone asks for a connection to a server ending with dev.rdc.library.northwestern.edu, run this script instead and pass it the hostname and port. That script then executes a series of steps. First, it extracts the hostname, in this case, MBK. It queries the AWS EC2 service for a virtual machine with a project tag equal to dev environment and an owner tag equal to MBK. On finding one, it checks to see if it's running. If not, it tells the AWS EC2 service to boot it up and then waits for it to be ready. Once the virtual machine is up and running, the script starts a server manager session connected to it, then starts the SSH server inside that session, and then hands the whole thing back to the SSH client to proceed as if it were a normal connection. This works regardless of how the SSH connection is initiated, as long as the process initiating it respects the system-wide SSH configuration. Another feature of the environment's configuration is the ability to shut itself down when idle. For our purposes, we define idle as we ran several checks and they all came back false. Those checks consist of looking to see if there is a Visual Studio Code server, code server running with an active listening port, indicating that a user is actively using their editor, an active tmux session running, indicating that the user may have started a long-running background process that they're going to come back to check on later, or as a catch-all, that a .keepalive semaphore file exists in the user's home directory. This catch-all allows the user to hold the system open even if other conditions aren't met. Note that the mere presence of an SSH connection is not sufficient to keep the system running. Here's how that works. When the system is running, it runs a script in the background once per minute. That script asks two questions. First, is there a shutdown scheduled? Second, should there be a shutdown scheduled? If the answers match, either there should and there is, or there shouldn't and there isn't, nothing happens because the desired state already matches the actual state. But if the system is idle and isn't already set to shut down, the script schedules a shutdown with a 30-minute countdown timer. If a shutdown is scheduled, but the system detects that it shouldn't shut down, it cancels the pending shutdown. This scheduling behavior lets us ask an easy question, is the system currently idle, with the option to change our minds later, instead of having to ask the much more difficult question, is the system currently idle, and if so, how long has it been idle? The last major piece of this puzzle has to do with users' ability to access services running in their own dev environments from a browser or other web client. Making sure that each environment always has its DNS name pointed at its dynamic public IP address makes connections much easier and also provides an address that matches our shared wildcard SSL certificate. Port forwarding over SSH through an SSM session turns out to be ridiculously slow. So instead, we have a convenient script that allows users to open and close specific ports in their system's security group, the AWS version of a dynamic flexible firewall, to one specific IP address, a whole network block, or to the entire internet. With our fully remote team, separated as much by internet routing as by geography, this also lets us collaborate easier by allowing us to share access to our services while in active development. Finally, we have a script that can connect a lightweight HTTPS proxy to any running service that doesn't support SSL natively. This is remarkably important to our distributed system of front-end applications, back-end services, and APIs, since it lets us run HTTPS end-to-end in the northwestern.edu domain to overcome issues with cross-origin resource sharing, same domain browser cookies, and Northwestern's central single sign-on service. So how did we build this? The first pass involved AWS's own Cloud9 service, which offers a collaborative browser-based development environment on a small persistent virtual machine. It worked reasonably well, and in fact, all of the developers except me are still using their original Cloud9-based VMs. And this talk may be the first time some of them are hearing about the changes to come. But creating the Cloud9 environment and grafting on support for Visual Studio Code required a large, complicated custom bootstrapping script and several hacky, brittle, non-standard customizations. These changes added extra steps, extra time, and a lot of potential extra error to the build process. Cloud9's defaults and assumptions also required making extensive changes to the system after it was up and running, enlarging the system's root volume, installing additional packages, including some from non-standard third-party repositories, and several other things that are far easier to do during the initial provisioning process. Cloud9 also offers a limited set of Linux distributions, none of which precisely met our needs, which required even more uncomfortably hacky customizations. The current version of the project uses Terraform infrastructure configuration files to provision all shared and individual environment resources, with all dependencies and required tools installed by an EC2 first boot user script. The startup and shutdown scripts are tailored to our specific needs, and the code can be adjusted to work with any Linux distro we might choose to use in the future. Other features of our remote development environment include a PostgreSQL-compatible Aurora serverless relational database that scales up and down in response to demand. Like the EC2 instances, we don't incur any costs while the database is completely idle and spun down. Each developer's SSH public keys are installed on their systems directly from their GitHub profiles, allowing for seamless authentication. SSH key forwarding allows developers to identify themselves to other systems, such as GitHub, from their dev environments without ever copying their private keys off their own laptops up into the cloud. A backup script that makes quick, complete backups of each user's home directory directly to an S3 bucket. The backup script ignores build artifacts, node modules, Ruby gems, Elixir packages, and other replaceable files. Installed versions of Node.js, Ruby, Elixir, and other language tools, as well as VS Code Server and any installed extensions, are also skipped during backup. But the backup script does record what was installed, and the restore script reinstalls all of it. The repository containing our custom scripts and tools is updated via git pull every time the user opens a shell, which allows us to propagate bug fixes and enhancements quickly. Environment-specific configuration is automatically pulled from AWS Secrets Manager, allowing configuration changes to propagate to everyone's systems with little effort. And we can set up, tear down, or rebuild an environment in a matter of minutes. All is not yet perfect, however. We still don't have a good automated solution to the developer forgets to shut down VS Code or exit their TMUX session on Friday afternoon problem, which has led to some machines staying awake well beyond when they should have been able to shut themselves down. The SSH key forwarding agent purges cached keys after 2 hours. We have a documented workaround for what to do when remote authentication fails, but it's clunky and it could be better. Once a system hits its shutdown point, you have to wait for it to shut all the way off before you can initiate a new connection and boot it back up. Due to a quirk in Cloud9's configuration, this shutdown can sometimes take several minutes. Fortunately, the new Fedora Linux-based VM that I've been using has a much shorter shutdown cycle. Visual Studio Code sometimes fails to connect on the first try. Clicking retry once or twice almost always solves the problem, but it can still cause a little bit of frustration in the short term. OpenSearch Cluster doesn't have an auto-scaling option the way Aurora Serverless Database does. And since it takes so long to stop and start the service, its 7.5 cents per hour cost is one of our highest month-to-month charges. Finally, some AWS features have costs that we didn't anticipate. Most are predictable, but some of my original VPC configuration led to higher than expected and unnecessary charges until I identified and corrected those issues. We can't only talk about fun, whimsical stuff like SSH proxies and port forwarding. Some of you would like to know what we're paying for all of this. The answer is less than we expected, coming in between $100 and $150 per month. May is an outlier as we were just getting started and not using the system regularly. As I mentioned earlier, OpenSearch is by far our largest immutable expense, while the virtual machines themselves make up the bulk of each month's variable expenses. As for cost per developer, we seem to top out around $40 a month individually, with the average coming in far lower than that. The shared infrastructure, mostly OpenSearch, still accounts for more than all of us put together. The two front-end developers still do quite a bit more work on their laptops than the back-end developers, which explains why some of these bars are so much shorter than the others. But even with everyone switched over eventually, I'd be surprised to see us top $200 or so in any given month. If you made it this far, you may be curious enough to ask questions or check out the code behind the project. Here's where you can do that. Thank you.
Thanks, Mike. There's time for a few questions. Looks like we have one.
Yes, I see that. Is the current implementation region independent to handle AWS outages? Not at present. We certainly don't have running like our standard services provisioned and running in multiple regions to let us switch over quickly, but the Terraform scripts that we have would let us stand up in a new region in probably a half hour or so if we needed to. Obviously, that doesn't help with any data we may have in our already in the database or in our indexes and S3 buckets, but we generally make a point of considering that stuff, ephemeral and throw away at any time anyway. So getting back up and running in case of a US East 1 outage wouldn't take us very long.